Hello.
Hello. Am I
Yeah,
audible?
yeah.
Uh, yeah. Okay. Okay. Yeah. So, good evening, ma'am, and good evening, everyone. Okay. So today's session, it's about revision of distributions. Okay. So, ma'am will revise the concepts of in week 11 and week 12, which cover the discrete distributions and continuous distributions. Okay, so it's a request to everyone. Please do not ask any doubt from activity or something practice assignment. Those kind of doubt we can discuss in our sessions. Okay, so if you have doubt in the particular concept, then you can ask at a time. So we'll take care of it.
Okay. Yeah.
So yeah,
Thank you.
yes, ma'am. Yes, ma'am. I
Am I
think
audible?
yeah, ma'am. Yeah, you are okay.
Okay. Just a minute. I'll just share my slides. Yes. Second. Yeah. Uh, Okay, Prashant, there are some questions regarding the exams. You can take that later. Okay.
Yes, ma'am. Yeah, sure, sir.
Yeah. So can I start?
Yes, ma'am. We can start.
I see only 32 participants. I'll start, right?
Yes, ma'am. Yes, ma'am. They are joining. So I
Okay.
think,
Right.
or also we can wait for 2 to 3 minutes. So wait.
Okay.
Okay.
You tell me. I'm okay with anything.
Okay, ma'am. I think we can start
Okay,
within two
sure.
to
Let's
three minutes.
start. Okay. Should
Okay, ma'am.
not
Yeah.
penalize people who joined on time.
Yes, ma'am.
Okay.
Yes, sure, ma'am.
Yeah.
Sure.
So, good evening, everyone. This session will be primarily a revision on concepts of probability distributions. I believe from Prashant that already there has been a revision on random variables, expectation, and variance. So, I'll just quickly run through those concepts because I need that continuity for me to set up the distribution part. So, the agenda is we'll have a very quick review of random variables and all of that. And you can always use the chat box for your questions. I am going to look at the chat box and monitor that. And if there are anything else, you can also check with Prashant. He's also here. So you can send him and he will let me know if I miss on any questions. And as told by him, if there are any questions pertaining to assignments or activity question, please refrain from asking here. This is only at a conceptual level. It is a review of concepts. It is not about doing the uh, 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 assignment or any question. Okay, right. So the main idea is when we are looking at probability, we start with what is called a random experiment. That is our basic uh, building block. And from the random experiment, we have defined what is called a sample space. But what happens is, many a time we might not be interested in knowing about just the details of the experimental result, but we are interested in some function of the quantity. That is, if I toss a coin twice, I know that this is my sample space. I might not be interested in the outcome itself, but I might be interested in the function of an outcome. And by function of an outcome, I mean that I might be interested in knowing how many times I get a head in every outcome. So I'm mapping every outcome to what I say is a numerical value. Similarly, when I roll a die, and this was the question that this was the example we discussed in the lectures also, I might not be interested in knowing whether the outcome was a 1-6 or a 2-5, but I might be interested in knowing what are the sum of the outcomes. So every outcome is mapped to a function or a real number value. Okay, right? Okay.
Yes,
So then,
ma'am.
hello, hello,
Hello, ma'am.
yeah,
Good evening.
yes. Can we restrict this session only to distribution? Because I think in the limited time we want to do this, we'll definitely take these questions otherwise. Okay.
Okay, ma'am.
Right. Thank you. Because I think this session is solely for distribution. I would like to restrict, because in the interest of time, we have only 2 hours. And in this time, I would like to only, because it's very easy to get carried away if we are not having the thing. Okay. So when we are looking at random variables, primarily the thing that we need to understand is, just as a sample space could have been even time taken. Okay, we could have a time which was 0 is less than infinity, and this was a sample space. Again, if I am tossing a coin and I'm tossing it till I get a first head, I could have a tail head, tail head. I could have countably many, incountably infinite sample space I could have. So you saw that we could have any type of a sample space, but here I'm not interested in the outcomes, but I'm interested in the function that maps every outcome to a real valued number. And this is what we refer to as a random variable. So I have random variables. I have a random variable which takes at most a countable number of possible values, is what I refer to as a discrete random variable. When their outcomes are numerical but cannot be counted. So typically when I have variables that are measurable, okay, I call that a continuous random variable, whereas a discrete random variable, I'll have points along a real number line. So the one way to remember is discrete random variable always involves counting, whereas continuous random variables always involve measuring. Now, if you go back to even when we talk about variables, we had discrete and continuous when we had numerical variables. So discrete is always counting, whereas continuous is always measurable. Okay, so that is the first distinction between a discrete random variable and a continuous random variable. The next thing is the concept of what is the distribution of the random variable. By distribution of the random variable, when I talk about a discrete random variable, I know x takes either x1, x2, it is taking discrete values. If it is finite, it will take x1, x2, xn. If it is infinitely many, it will take x1, x2, x3 so far. Whereas if in a continuous variable, my x will belong to an interval. So in a discrete case, I'll have x taking discrete values. In a continuous case, I'll have x belonging to an interval. So I'm interested in, this is if it takes finite number of values, this is when it takes infinite number of values, and x belongs to an interval if it is a continuous random variable. So what are we interested in? We are interested in I know these are the values this x is taking. The question we are interested in is what is the probability of x taking any value, or what is the probability of x belonging to an interval. This interval could be any A or B, or it could be any C, D interval also. That is, what is the question that we are trying to answer? For example, if I had the sample space of HH, HT, TH, and TT, I know that I can map, and I'm counting x is the number of heads. This will be a 2, this will be a 1, this will be a 1, this is a 0. I know x takes the value 0, 1, 2. So I might be interested in knowing what is the probability x is taking the value 2, or x is taking the value 1, or x is taking the value 0. On the other hand, if I'm counting the time taken for a particular thing, that time could be in an interval which is say 2 minutes to 10 minutes. I might be interested in knowing, okay, what is the chance that this x is less than or equal to 5 minutes and it is greater or equal to 3 minutes. Or in other words, I'm interested in knowing what is the chance that x belongs to the interval 3, 5. So you can see that depending on the context of the problem, we need to understand whether we are having a discrete random variable or a continuous random variable. Till here, is it clear? What is a discrete and what is a continuous random variable?
Yes,
Yes,
ma'am.
ma'am.
Yes,
Okay.
ma'am.
So the
Yes,
next thing
ma'am.
is, so the first is understand what is a discrete versus continuous. The next thing is, when we are looking at it, we know what is a probability mass function if it is discrete. When it is continuous, it is called a probability density function. So probability mass function is probability x takes a value xi. On the other hand, a density function, which is f of x, is integral over an interval. Okay. And I know that it will take some function such that this integral over the interval I've defined it is always going to be equal to 1. This is basically probability x. This is an integral because this is a equality. This is an integral. This is a continuous function. The probability x equal to xi is a discrete bar, whereas f of x would be a continuous function. Okay. So this is what we refer to as a probability density function and a probability mass function. So whenever we talk about discrete variables, the first thing is we need to know what are the values the variable takes, what is the probability mass function if it is a discrete random variable, what is the probability density function if it is a continuous random variable. Then we have the concept of a cumulative distribution function. The cumulative distribution function, as the name suggests, is if x takes values x1, x2, which are ordered, and I would like to know what is the probability x is less than or equal to 5, I add up all the values. I add a probability x equal to x1 plus probability x equal to x2. So I'm accumulating it till probability x equal to y, and that is what gives me the cumulative distribution function. Now, what is the equivalent in a continuous case? Now, x1 equal to x2, all of these are continuous here. So this would be integral of whatever is the range. If I'm having a y 0 to y, f of x dx, that would be the cumulative distribution function in the case of a continuous random variable. In the case of a this one, it is going to be probability x is equal to xi for all those xi less than or equal to y. So this is the next concept that you need to know is what is a cumulative distribution function. Now, typically when we talk about distributions, we refer to this distribution x. We tell what is the probability of x equal to x if it is a if it is a discrete, x belongs to an interval if it is a continuous random variable. This is what we refer to as probability mass function. This is probability distribution function. We define the cumulative distribution function for both. And then we have the notion of expectation of the random variable and variance of the random variable. So in today's session, we are going to look at a few discrete distributions and a few continuous distributions. When I talk about discrete distribution and continuous distribution, the focus is when would I refer to a distribution as a discrete distribution? What is the clear cut? That is, what distribution would be the most appropriate? What are the assumptions and when will it fail? That is how we are going to look at it. Any questions so far, please?
No, ma'am.
Okay.
What's
Ma'am,
clear?
expected value is the mean value.
I wouldn't say expected is the mean. Expectation is always what we refer to as the long run average. Okay. Because what is an expectation? The way we define expectation is, suppose you are conducting a random experiment again and again. Okay. In expectation, what would you expect that random variable to take? So if you look at it, the example we saw also, if I toss a coin, what are the possible outcomes of the coin? It is X and T, right? So suppose I map H equal to 1 and T equal to 0. And what are the values this X is taking? It is taking the value 0 and 1. It is a fair coin, so the probability is half and half, right? So what is the expectation of this? It is 0 into half plus 1 into half, which is a half, right? But what is the value this X is taking? X is taking the value 0 or 1. So what does it mean that this expectation is half? It doesn't mean that you keep tossing a coin, at some point of time you're going to get both head and tail, because that is what half would mean. Agreed?
Yes.
But if I assume that this X is mapped to 0 and tail is mapped to 1, okay, the long run average of the 0 and 1 would be half. That's what it means. Is the concept clear?
Yes, ma'am. So, ma'am, in many questions they gave the mean value. So, what we have to take then?
Yeah, so I'll tell you what is the thing is, the mean, it is a long run average. It is that is why we always tell that the parameters of the distribution are expectation and variance, which is the same as the mean and the variance. You can equate it, but it is not the actual average. It is a long run average. That is a conceptual understanding. Is that clear?
Yes, ma'am.
Excuse me, ma'am.
Yeah.
Ma'am, for cumulative distribution function for continuous variable, it is defined from minus infinity, right?
It depends on the range of the random variable. Okay. For example, if I'm talking about a random variable which will take values only between 0 to infinity, okay, then the cumulative, okay, a cumulative distribution function, the domain is always between minus infinity to infinity. Okay, it's defined for all x.
Yes,
Okay.
ma'am.
It is probability x is less than or equal to x, and it is defined for all x which is between minus infinity and plus infinity. But since it is a probability, the range would be 0 to 1. Is that clear?
Yes, ma'am.
Yeah, it is defined for everything. See, for example, again, if I have this value of this x, 1 second. Suppose I go back to my example here. My sample space is head and tail. Okay, I'm mapping this to 1 and this to 0. Would it make a difference if this were a 0 and this is a 1?
No, ma'am.
It wouldn't make, because I'm just mapping it, right? This x is taking value 0 and 1. I need 0 to be less than or equal to 1. Can I define f of minus 1? Answer is yes, it will be 0, right? So f of x is equal to 0 for all the small x which is less than or equal to 0. At x is equal, strictly less than 0. At x equal to 0 is taking the value half, is less than 1. Then it will take the 1 for x is greater or equal to 1. Does that make sense?
Ma'am, actually, I'm asking for continuous.
For continuous also, it would be the same. Suppose I'm having a sample space which is between 0 to infinity. Okay, that is the time taken to reach.
Yes, ma'am.
Okay, so then I am having a distribution function, right? Till that point, it will be 0, and then it will take another value. Let me tell you, suppose we'll come to uniform and I'll discuss all the cumulative specific examples, okay?
Sure. Thank you.
Right. So the first point is, when would I have a discrete distribution and when would I have a continuous distribution? Remember, again, discrete is whenever I have a count. A continuous is whenever I have a measure. Okay. Sorry. Okay. So for example, if I'm asking number of people, number of times, number of accidents, typically I am referring to a discrete random variable. Whereas when we are referring to what is the speed or time or temperature or height, it would be a continuous. So depending on the context of the question, you need to understand whether it is a discrete random variable or a continuous random variable. So whenever I talk about a function, we have just talked about the discrete and expectation and the variance. So I'm going to go to the simplest of the discrete variables, which is called a Bernoulli random variable. A Bernoulli random variable takes on a value which is just two values. Okay. And I can map that to 0 or 1. So a Bernoulli experiment is an experiment which has just two outcomes. Okay. Now, again, the thing is, can I define, should all my experiments be just a Bernoulli in the sense that should I have only two outcomes? It is a random variable which will take either the value 1 or 0. Okay. And that is why I call it a Bernoulli random variable. For example, if I have a roller die and I have 1, 2, 3, 4, 5, 6 are my outcomes, can I define a odd and a even? This would be, if it is an odd, I'm going to give a value 0. If it is even, I'm going to give a value 1. So this is mapped to 0. This is mapped to 0. This is mapped to 0. This is mapped to 1. This is mapped to 1. So I have this random variable which is taking only two values. Is that clear? So is that a Bernoulli random variable?
Yes.
Yes,
ma'am.
ma'am.
Okay, so it is not the outcomes are 0. It is a random variable which is taking two values. So when I have a Bernoulli experiment, it takes either the value 1 or 0. So I can assume that it takes the value 1 with a probability P. This is typically rated as a success, and this is what I call a failure. So the probability with which it takes as value 1 is P, then this would be 1 minus P because it's taking only two values. So the expectation, so I write X is a Bernoulli random variable and the parameter is P because I know that it takes a value 1 with this parameter P. So this parameter has to be specified. Is that clear? Okay. So whatever is the parameter P, I know the expectation is going to be 0 into 1 minus P plus P. The expectation of Bernoulli random variable is P. What would be expectation X square? What are the
That is
values X
same.
square can take?
P.
Same
That
P.
will also take 0 and 1. Expectation X square is also P. So what would be variance of X? It would be P minus P square, which is P
P1
into
minus P.
1 minus P. So when I'm talking about, again, what is the PMF? The probability mass function is this. What would be the CDF? The CDF is going to be till it comes to the value 0. Okay. So what is the CDF of the, 1 second, sorry. Yeah. The CDF of the Bernoulli random variable is, it's taking only two values. Till it is 0, it is going to be at 0. At this one, it would be 1 minus P. At 1, it would be P. And this would be the cumulative distribution function. Expectation is P. Variance is P into 1 minus P. The next is this discrete uniform random variable. One of the most popular examples is I roll a die. What are the values? And I'm just mapping each of the rolls to the number it is. I see number of dots. So what are the values this random variable is taking? I'm just mapping each of the values to the
1 to
number of
6.
dots I see in the die. So what are the values this random variable is taking?
1 to 6.
1 to 6. And it's a fair die. Okay, so what is the probability x equal to I? This would be
1
a
by
1 by
6.
6, 1 by 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 6. So if x takes a value 1 to n, and the chance of x taking each of the values is the same, equally likely to happen, then that is called a discrete uniform distribution. And you can see that the PMF, the graph of the PMF is it takes values 1, 2, 3, 4, 5, and 6. All of them would be bars of the same height. Okay. Now, what would be the CDF? Again, till it is 1, it would be 0. At 1, it would be 1 by 6. This would be 1 by 6, 2 by 6. This would be 3 by 6. This would be 4 by 6. This would be 5 by 6. And it's going to be 1. This would be my cumulative distribution function. This is going to be my probability distribution function. Is this clear as to what is the probability mass function, probability mass or probability distribution function, and the cumulative distribution function?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Ma'am, just
Yes,
one
ma'am.
doubt. How to convert a PMF into CDF?
What is PMF? PMF is just PMF and PDF are the same. Only thing
No,
is
ma'am, CDF. How to convert PMF into CDF?
no PMF. See, the main thing is when you're talking about a discrete distribution, you can imagine that as masses, that this point has a mass. Okay, that's why it's called a probability mass function. Whereas in a density, in a continuous distribution, I don't have x taking a particular value. I have x belonging to an interval. Is that first conceptually clear?
Yes.
Okay. So when I'm asking what is the weight of x belonging to xi, that's why I'm asking what is the probability mass function when I'm, see, both of them are distribution functions. Okay, probability distribution function, not cumulative probability. In a discrete case, I refer to it as a probability mass function. Many books refer to as probability distribution function also, but this is the distinction which I just want to have. Because it is a mass, I can talk about x taking a value xi when it is a discrete distribution. Whereas when it is a continuous distribution, I can only talk about x belonging to an interval. Is that clear? Is
Yes,
it
ma'am.
so?
Yes, ma'am.
I'm interested.
Yes,
So if I
ma'am.
have the density defined, this will be the area under the curve if x belongs to a particular interval. Is that clear?
Yes, ma'am.
Okay. So that is the distinction. So whenever you have a discrete distribution function, I expect the random variable to take the values 1 to n with equal probability. So what would be the expected value? It is going to be 1 into 1 by n plus 2 into 1 by n. And you know that would be n plus 1 by 2. We can verify that if x takes the value 1, 2, 3, 4 up to 6 with 1 by 6, 1 by 6, the expectation of this is nothing but 7 by 2, which is 3.5. I think we have done this many times. Similarly, the variance of a discrete random variable also can be found out, that you can use the expectation of x square. Now, x square is going to take the value 1, 4 up to n square. I can use this one of 1 into 1 by n plus 2 square into 1 by n and n square into 1 by n. You can find out computationally, you know what is the variance of this random variable. The next is hypergeometric, but before I go to hypergeometric, I'm going to talk about what I mean by the binomial random variable. The binomial random variable is one of the most important discrete random variables. The reason is when a lot of situations where I have independent and identically distributed trials, Bernoulli trials, I can model it as a binomial distribution. So what do I mean? So when I want to do a check for a binomial distribution, I need to be first of all, I need to understand whether the experiment is a binomial experiment or not. Now, what is the binomial experiment? For binomial experiment, I need to verify whether my trials are independent and identically distributed. Okay. So I toss a coin once. Is that a Bernoulli trial? Tossing a coin once?
Yes, ma'am, it is.
Yeah. So that is a first binomial. I toss a coin twice. So this is toss 1. This is toss 2. Is toss 1 a Bernoulli trial?
Yes, ma'am.
Toss 2 a Bernoulli trial?
Yes, ma'am.
Yes,
Yes,
ma'am.
ma'am.
Now, what is the probability of me getting a head in toss 1?
Point
What's their
five.
coin?
1 by 2.
Half. What is the probability of getting a head in toss 2?
Point
1
five.
by.
So is the probability of getting a head in toss 2, does it depend on whether I had a head in toss 1 or not?
No.
No, ma'am.
So
No, ma'am.
because getting a outcome in toss 2 is independent of whether I get a outcome in toss 1. Now, similarly, the probability of getting a head in toss 2 is the same as probability of getting a head in toss 1. So the first thing is the independent part. Since the probabilities are same, it's an identical distribution. So a collection of IID Bernoulli variables is what we call a binomial distribution. Now let me tell you another experiment. I have 5 balls, okay, of which 3 are blue and 2 are red. I am picking up a ball at random. Okay, what is the sample space for this experiment?
5.
And noting the color of the ball.
5.
What is the sample space? I'm picking up a ball at random and I'm noting down the color of the ball. So what are the outcomes of this experiment?
Blue ball or red ball?
3 blue, 2 red.
2 ball or a red
Red
ball.
ball.
Okay. Yeah. What is the probability of it being a blue?
3 by 5.
3 by 5.
By 5. So these are not equally likely, right? Okay. Now I'm repeating the experiment. So in the first thing, I could have a blue or a red. Okay. In the second time, I'm replacing the ball. Okay. I'm replacing the ball. So what is the chance that it would be a blue? Second, this one, draw.
3 by
Same.
5.
3 by
It
5,
would
2
be
by
same. Right? Again, these are, so is this a Bernoulli experiment? Is the
Yes.
first draw a Bernoulli
ma'am.
experiment?
Yes, ma'am.
Yes,
The second also a Bernoulli?
Yes, ma'am.
Yes,
Now
ma'am.
I don't replace the ball. Okay, I don't replace the ball. So initially, how many balls did I have?
5.
5.
Five.
What is the probability with which it was a blue?
3 by 5.
Now what would be the probability here?
2 by
2 by 4.
2 by
2 by 4.
What would this be? This is also 2 by 4. What would this be? 3 by 4. This would be 1 by 4. Is that right?
Yes, ma'am. Yes, ma'am.
Yeah. So are they identical? The chance of you finding, are they independent and identically distributed?
No.
No, ma'am.
No,
So
no.
can I model this as a Bernoulli binomial experiment?
No.
No.
So what I want you to see is this is equivalent to getting a head or a tail because the outcomes are only 2, right? But you can see that it is failing this independent and identically distributed assumption. So the first thing is whenever I want to apply a binomial distribution, I need to verify that the following. That is, I have n independent trials. Why is this n important? Again, I keep tossing a coin till I get a head. Okay, what is my sample space?
Head or a tail.
H,
Head.
TH, TTH.
I'm tossing a coin till I get a head. So the first toss is a head,
PH,
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 TH.
TTH, and so
and
on.
so forth, right? Okay. Now I'm going to count the random variable is the toss in which I get the head. What are the values this X is taking?
1 to infinity.
1,
1,
2, 3,
2,
so
3,
on.
4, and so on. Okay, right. So now what is the probability with which I get a head? It is P. This would be 1 minus P into P. Is that right? 1 minus p square into p. See, this is how I am getting the number of. Is that clear? But x is taking infinitely many values. Is that clear?
Yes, ma'am.
Yeah. So this is not a binomial distribution because I do not know what is the total number of independent trials that I could have infinite number of trials before I land up in a head. Is that clear?
Yes, ma'am.
Yes,
Yeah.
ma'am.
Yes, ma'am.
So when I talk about a binomial random variable, the things I need to understand is I have n independent and identically distributed trials, and I need to know what is the probability of a success. If P is the probability of a success, 1 minus P is the probability of failure. This random variable X is then written to be a binomial random variable with parameter N and P. Is this clear?
Ma'am,
Sorry.
but the previous example was an in identical experiment as the first. If I toss once, then then the probability of head comes.
Yeah, so
Uh,
the probability of getting a head or a tail was identical, but it was not a binomial experiment because I do not have n independent. I do not know the number of trials, right?
yes, ma'am. But ma'am, in the sample space there, if I toss twice and if I toss thrice, the number of heads, probability of
See, the
heads coming,
probability
then
of a
it's not
success,
equal.
right? Probability
Oh,
of a success was the
okay.
same, right? Whether it was a head, tail, or head, the probability of you getting a head was the same. But the probability of the outcome happening was different. Is that clear? The probability of this
Oh,
outcome was
okay.
1 minus p square into p. Is that clear?
Yes, ma'am. Yes, ma'am. Clear.
Sorry,
The
ma'am.
probability of success was the same, right?
Yes, ma'am. Yes,
Is that
Sorry,
clear?
ma'am.
yes,
Jumping.
ma'am.
Sorry, ma'am. Jumping the gun a
So
little.
when you are
But
talking about a binomial random variable, the parameters of the distribution are this n. So I need to know what is this n. I need to know what is the probability of success. Let me share the Excel file to just show you how to it is not from an examination point of view, just to identify. Is the Excel visible, please?
Yes.
Yes, ma'am.
Yeah. So whenever I give a problem of this kind, okay, so here you can see that. Second. Yeah. The problem is 5% of all DVD players manufactured by a large electronics company are defective. A quality control inspector randomly selects 3 DVD players from the production line. What is the probability that exactly one of these 3 DVD players is defective? So first of all, is it a binomial experiment? What is the Bernoulli experiment here?
It would be
Defective or
either defective or
It
not
is either
defective.
defective or good, right? These are the outcomes. What is the chance with which it is defective?
5 by 100.
0.05,
0.5. So what is the probability it is with which it is good?
0.95.
It is 0.95. Till here, is it clear? Okay.
Yes,
How
yes.
many are they choosing from the DVD line, production line?
3.
3. So what is that? N. What is my N? That is equal to
3.
3. And what is my random variable here? This random variable is counting the number of defective in among these 3. Is that clear?
Yes, ma'am.
Yes. Yes,
Right?
ma'am.
So if I have to identify this parameters of the distribution, I know that X, which is the number of defective, is a binomial experiment with N equal to 3 and P equal to 0.05. Is that clear?
Yes,
Uh,
yes, ma'am.
Ma'am,
Now,
Yes,
suppose,
ma'am.
yeah,
ma'am, here it is given that 5% are defective, right?
yes.
So after choosing the first, if one defective is gone into the first, then while choosing the second one, so our that percentage of
You're choosing
defective.
only one. No. See, what is happening is I'm choosing 3. Okay, DVD players. I have DVD 1, DVD 2, and DVD 3, right? Okay.
Yes, ma'am.
What is the chance with which D1 is defective?
0.05.
0.05. What is the chance with which D2 is defective?
0.0.
I've already chosen this 3.
Okay,
Right?
okay. Yes, yes.
Now
Okay,
the
ma'am.
chance with which D2 is defective does not depend on whether D1 was defective or not. Will it depend?
No,
Ma'am.
Okay. Okay, ma'am.
Is that clear? I've
Okay,
just
ma'am.
chosen these 3.
Okay, ma'am. I thought if you are already choosing the defective one,
No, I have not chosen the defective ones. If I chosen the defective ones, then the probability that exactly one of them is going to be defective is going to be 1, right? Because now it would be 0 because I have chosen all the 3 to be defective, right?
okay, 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 ma'am.
Is that clear?
Okay, ma'am. Got it. Yes, ma'am.
Is that clear?
Had it been one after the other, will it change?
Pardon?
Had it been selected one after the other,
Which see the problem is I'm not told you that I am choosing. See, I'm not telling I've chosen. I've just chosen 3 defective I have chosen 3 DVD players, right? So we are not saying that I have chosen this. I've seen whether it is defective or not, and then I'm choosing D2. That is not what I'm trying to say.
okay.
I've chosen 3 DVD players. Among these 3, I want to know what is the chance that exactly one of them is defective. Okay. Now, what is this random variable X? This is counting the number of defective players among these 3. What are the values that this X can take?
0, 1, 2, 3.
Either none of them are defective, in which case it will take the value 0. One of them is defective, 2 of them is defective, or 3 of them is defective. Is this clear?
Yes, ma'am.
Yes.
Yes, ma'am.
Yeah. Now, what is the probability with which it's defective? So I know that the probability mass function for a binomial is n choose I, p raised to I, 1 minus p raised to n minus I. So you can see that that is what we have found out here. Okay. So you can see that Excel has an inbuilt function, and that inbuilt function is nothing but, so it is important for us. So if you look, can you all look at what is this binom.dist?
Yes.
Yes,
And the
ma'am.
parameter is, you'll have to tell what is the number. So what are the values this is taking? It is taking the value 0, 1, 2, 3. Number of trials. What was the number of trials? How many Bernoulli trials did I have here?
3.
3. What was the probability? Because that is the parameter, right? What is the probability?
0.05.
It is 0.05, and then cumulative. If I put a cumulative as 0, I'll get a probability mass function. So let me just show it to you. This is my probability mass function. Okay. Now for the same thing, if I'm going to put a cumulative which is 1. Okay, let me copy this. This is the probability mass function. Okay. And let me, sorry. Okay, and here if I put it as 1, what is probability X is less than or equal to 0? It would be the same. Probability X is less than or equal to 1. What would be probability X is less than or equal to 1?
Both will add up.
It will add up both,
yes,
right? So you can see it is 0.99, X less than or equal to 2.
Will add up.
Even this,
Add the second one.
right? And less than or equal to 3, you can see it would be a 1. Is that
1.
clear? So this would be
Yes.
the cumulative distribution function. Is that clear?
Yes.
Yes, ma'am.
Yes, ma'am.
So given any problem, what you need to understand is, okay, so if it is a binomial problem, identify the n and the p. This is the key thing, that once you identify these two, then you can actually find out what is the probability mass function. You can find out what is the probability cumulative distribution function, and you can answer all questions now. What is the chance that, okay, what is the chance that I can find more than 2 defective players?
Probability of 2 plus probability of 3.
That would be probability of 2 plus probability of 3, or it is going to be 1 minus probability of this one, right?
Yes.
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 Is that clear?
Yes,
Yes.
ma'am.
Now,
Yes,
can I
ma'am.
flip the question and ask you what is the chance that everything would be a good? All the three would be good?
Yes, ma'am.
What is the chance that all the three would be good?
Probability
Is
of 0.
probability of x
0.08.
is equal to 0.
0.00123.
0.857.
375.
Probability x equal to 0, and that is also equivalent to what
All
would be
are
the,
good.
it would be
1
this
minus 3.
0.95 into 0.95 into 0.95 also, right?
Yes.
Is that clear?
Yes, ma'am.
Yeah.
Yes,
Okay.
ma'am.
Right. So the first thing is, when you have a binomial distribution, the key thing is identify whether it is identical, independent distribution, and then you apply the formula. What is, on an average, how many defectives can I expect to find?
Ma'am, you are very likely to find no defectives.
On an average, what is the expectation of the binomial random variable?
N into P.
5 in 100.
So what is n into p here?
3
Zero.
3 into 0.05.
3.
What is that? So
0.1.
it is, I would expect to find on an average 0.1. So what does this mean on an average? So it is not the mean number of averages, right? If I continue to do this experiment for sufficiently long number of time, this is the expected number of defects I will find when I am going to sample 3 DVD players. What would happen instead of 3 had I taken 30? What would happen to my average?
1.5, ma'am.
It would have become
1.5.
1.5. And it means it looks so this one, right? If I'm sampling more, right? If I'm sampling more with the same probability, 5% of the DVD players, if I'm sampling more, if my sample size increases, right? Then on an average, I would expect to find 5%. What is 5% of 30, right? Is it clear? 1.5 of them would be
Defective.
defective. Is it clear?
Yes, ma'am.
Right? If I taken 300,
It would be 15.
again,
Yes,
that is
ma'am.
5% of that 300, right?
Yes.
Does it make sense now?
Yes.
What is the,
Yes,
this
ma'am.
one of the expected value?
Yes, ma'am.
Yes,
So
ma'am.
it all depends. So even though that is a 5% of all DVD players, then what is the value X would take if I had 300?
Ma'am, 0 to 300.
But see, that is a problem. When my n becomes very, very large, then the values as X is taking becomes very, very large, right? So then I might want to see that whether binomial is appropriate or can I have some other distribution. And that's where we move from when n becomes very, very large. Suppose I have 30,000 sample. Then my n becomes very large and I'm looking at number of defectives in a very large space, right? Agreed?
Yes, ma'am.
Yes, ma'am.
So
Yes,
then
ma'am.
I might not feel that binomial seems to be appropriate. I might want to go for some other distribution. Is that idea clear?
Yes.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
But this formula will still give the answer, right?
It will give you, but I'm trying to see that whether it is appropriate to model. Just let's not go only by formula. Let's try and understand what would be more appropriate. Is that clear?
Yes, ma'am.
Right. So now the next distribution is what I am having here. I'll just tell you what is, just read that for a minute and then see, tell me which of the condition is violated. I have a manufacturing which makes auto parts that are sold to auto dealers. Last week, the company shipped 25 auto parts and it found 5% of those parts were defective. By the time the company manager contacted the dealer, 4 auto parts had already been sold. What is the probability that 3 of those 4 parts were good and 1 was defective? Is this again a binomial distribution? If yes, how? If not, why? Just read that question. I'll give you a couple of minutes. Read it. Again, what are the 2 possible outcomes that I'm looking at here? And how is
Defective
it
and
different
good.
from the earlier thing?
Defective and good.
It is defective and good. Even earlier I had defective and good only, right?
Yes, but ma'am, this is not independent.
So that is the important thing that we need to understand. Is that clear? And where am I losing? What is the chance of it being defective?
5 by 25.
0.2.
It is 5 by 25, right? That is the chance it's being defective. What is not independent here? Again, I'm asking, so what is it that we are asking? What is the probability that 3 of the 4 parts are good parts and 1 was defective? That is what we are asking, right? So
Yes.
I have a huge thing. So let me share my PDF. Okay, so when I'm moving over to the next distribution, okay, so here, if I, let me again, so here I am randomly selected n items from a set of capital N items, M of which are of one type and N minus M are of another type. So let's go back to this example. 1 second, I'll try and minimize this Excel sheet and share both of them. Okay. Are you able to see both the Excel and the PDF?
Yes, ma'am.
Yes.
Okay, let me do one thing. Yeah. So this is the problem. I have a manufacturing which makes auto parts last week. Okay. So what is capital N in this problem? What is small n?
Capital N is 25.
25.
Small n is 4.
So
Yes.
what is the, so what are the, so here I have B, 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 W, W, W. So what is this here? I had 25. This were
B is
defective,
defective.
defective, good, good, good. How many were defective?
5 by
5.
25.
So I had 5 were defective. So how many were good?
20.
20 were
20.
good. And how many did I send?
4.
What is the small n?
4,
How
ma'am.
many?
4.
I sent 4. Okay. And I want to know what? What is the small n? So what are the possible values this x will take? That is out of these 4, x is the
3.
number of defectives. So what are the possible values this x will take?
0 to 4.
Yes,
What
0
does
to
x
4.
equal to 0 would mean?
all are good.
All are good.
None are defective. Yeah.
Okay. X takes the value 0, 1, 2, 3, and 4. Okay. Now suppose I flip it. I have 20 here and I have 5 here. Okay. And I'm again taking n equal to 4. And I'm checking the number of good items. What are the values this x would take again?
Same.
Same, ma'am.
Same. Okay. Suppose I had here 3 and this is 22. Okay. And I'm again taking 4 items. What are the values x would take now?
Still same.
0, 1, 2, 3.
0, 1, 2,
X
0, 1,
equal
2,
to
3.
0 would mean what? So again, let me write this. This is 25. Okay. I'm having 22 good and 3 bad. And I'm taking 4. Okay. So what are the value? I'm counting the number of good items here. So what are the values x can take?
0, 1, 2, 3,
1,
X
4.
equal to 0 would mean what?
None of them are
4
defective.
bad items.
X equal to 0 would mean?
4 defective.
So what are, how many defectives did I have in the original?
3, ma'am.
3, ma'am.
So can X take the value 0?
No, ma'am.
No, ma'am.
Is that clear, the concept?
Yes, ma'am.
Yes.
Yes, ma'am.
Is the concept clear?
Yes, ma'am.
Yes, yes, ma'am.
Yeah.
They can't
So that
take.
is something which you need to understand. Is that concept clear?
Yes, sir.
Yes, ma'am.
Okay, so again, another place where the hypergeometry could be similar to what we discussed earlier, where I don't have an identical and independent trial. So you can see that in this, I start with a bag of 4 white and 3 blue balls. I pick up a ball at random. A blue ball is picked up in the first throw with probability 3/7, a white with 4/7. And if I get a blue ball, I'm going to, actually I retain with 4 white and 2 balls. Here it would be 3 white and 3 blue balls, right? So the probability changes. So you can see I don't have an identical and independent distribution here, though the values that X will take is 0, 1 and 2. Is that clear?
Yes,
Why
ma'am.
is the value of X equal to, what is this X counting again? This is a BB, this is a BW, this is a WW. Both are white balls, both are blue. This is a blue ball and a white ball. This is a blue ball and a blue ball. Is that clear? Yeah. But this is not a binomial experiment because I don't have a identical and independently distributed distribution. Any questions here, please?
Ma'am, in the previous question,
Yeah.
the throw means the number of defective pieces were independent of each other, but the probability was not identical. That's why we use
Yes.
hypergeometry, right?
Yes. Yeah. Okay. That's the problem. Yeah. So
Yes.
the probability of success is not the same, and even though the trials are this one, you're actually sampling from 2 groups and you're interested in only 1 group. That is what a hypergeometric. So if you want a hypergeometric to work, it should be dividable into 2 populations, black balls and white balls, and it should have changing probabilities of success. And that's why the binomial does not work, even though you're counting the same thing, right? Number of defectives, but I know that because I'm having it as 2 different subsets, the probabilities are not the same. Is that clear?
Ma'am, even if one of the conditions are violated, so we have to use hypergeometry.
Yeah, it won't. Your binomial will not work, right? For binomial to work, I need independent and identically distributed Bernoulli trials. Is that clear?
Yes.
Yeah. So that's why, see, when you look at this binomial, so what are the parameters of a hypergeometric? I need to know what is the small n. I need to know what is this capital N and what is this M. Okay, so the parameters are, every time I specify it with N, small n, and M. Is that clear?
Yes.
Yeah. Okay, so the expected value is N into M by N. Now let's look at only this M by N. N was my sample size.
Yes,
right?
ma'am.
Yes.
What is this M by N? It is the proportion of defectives in my original population.
Yes.
Yes,
right?
ma'am.
So this N into M by N, in some sense, you can view it as a N into P.
Yes, ma'am.
That is your binomial, this one. Is it
Yes,
clear?
ma'am.
Yes.
Yeah.
Yes.
Whereas you look at the variance, okay? In the variance, what you see here is this is N into M by N. This is 1 minus M by N. N into P into 1 minus P, and I have a finite correction factor. It is not the same as, what was the variance of a binomial? It is N P into 1 minus P, right?
Yes.
Yes, ma'am.
Agreed? So I can write this as 1 divided by N by N, 1 by N. So if this N is very, very large, this term will go to 0. If N is very, very large.
Yes, ma'am.
Agreed? Or this term would actually, so what happens is, you can see that if I have N equal to 20, M equal to 4, this is the distribution. I'll just show you this distribution. You can see this, the blue is binomial. For N equal to 25, what is M by N here? My N by, so I'm saying that N into M by capital N. What is my M by M? M into capital N in this case? Sorry. M by capital N?
0.5.
0.5. So you can see both the binomial and the blue is binomial and red is hypergeometric. Both of them are exactly the same.
Yes, ma'am.
Yes.
Is it clear? So you can look at this also. What is my m by n here? It is again 0.5. And you can see here again, it is almost it looks the same, the binomial and hypergeometric. Yeah.
Yes, ma'am.
Yes, ma'am.
Right. Now you see this n by n. So that is not only your n into m by n. You look at the n by n, small n by capital N. 5%, 50%. Here you can see that as my n increases, I know that my binomial. So this is my binomial. Okay. This blue thing is my binomial. As my n increases, I know that at some point it will take a binomial shape. That we know this is from the central limit theorem. I'm not going to go into that, but you can see that as n increases and your n by capital N, 50%, you can see that the shapes of the distribution, the mean appears to be the same, but the variability is different. Is that clear? The mean of the distribution, you can see it is the same, that n into m by n. That's why I said the mean appears to be the same. Is this clear, please?
Yes.
Yes, ma'am.
Okay. So the binomial versus hypergeometric, one of the things which you need to understand is in a hypergeometric, I don't have identical and independent trials. Binomial, I have independent and identical trials. The next important distribution is when I
Sorry,
want
ma'am.
to know the number of events in a fixed interval of time or space. For example, if I'm interested in knowing the number of misprints in a book. So this is the number of events happening in a space. The number of defects in a sheet of paper. Again, number of defects. I'm not looking at the number of defects in so many times, whereas I'm looking at in a sheet of paper. Again, space. Number of accidents happening in an interval of time. Number of vehicles entering a campus in an interval of time. So when I'm looking at the distribution, again, I'm counting the number, but I'm looking at it either happening in an interval of space or interval of time. This interval of space or interval of time could be continuous, but what is the random variable? It is the number of events happening. Is this clear?
Yes.
Yes, ma'am.
Yeah. I'm looking at the number of events that occurs either in an interval of time or space. In that case, this X is what we call, it follows a Poisson distribution. The parameter is lambda. So what is a Poisson distribution? Again, I'm looking, I do not know what is, so it happens average number of lambda events per interval. Then this X is a Poisson distribution where probability X equal to X is e to the power of minus lambda, lambda to the power of X by X factorial. So let me show you this example. Is the Excel sheet visible? Yeah. So here
Yes.
I'm saying that I'm looking at a distribution where the average is 0.9. Okay. So you can see that if the average lambda is 0.9, then my distribution is e to the, so again I go to Poisson distribution. When I do a Poisson distribution, the parameters of the distribution is, it is asking X. X is what is the value of the distribution, which is 0. The mean is 0.9. Okay. And again, I put a 0. So this is probability X takes the value 0. What I want you all to see is the following. If I am looking at the shape of this distribution, okay, for, let me put the value here, lambda, the value of lambda, which is nothing but the average value. Here I have, sorry, lambda. The value of the lambda in this case is 0.9. Okay. So let me link this to my B1. Sorry. Okay, and as always, what should the sum of this add up to?
1.
These are not the only values it is taking. It would not exactly add up to 1. Just a second. One second. So you can, one second, there's some problem. One second, this is some problem. X equal to 0 is this. Okay, so it is a 0.99 because the idea is it can take a value 7, but it is going to become very, very less, right? The probability. So if I plot the PMF, okay, if I just go ahead and plot the PMF, so what are the values X is taking? X is taking the values 0, 1, 2, 3, 4, 5, 6. If I go and plot the probability mass function, okay, you can see that this is the probability mass function. So at X equal to 0.9, you can see that the value of this e to the power of minus lambda. So this is the probability mass function. Is that clear? Can it take the value 7? Yes. But what is the chance with which it takes the value 7? The probability of average defective, it is going to be very, very less. That's why it is not adding up to 1. Is that clear? X can take value 0, 1, 2 up to infinity. That is the value. But the probability that X is greater or equal to 6 is very, very small. Is that clear? Now, suppose this was a 0.8. You can see that these probabilities are changing. Right? What would happen if it was a 0.1? You can see that from here itself, the probability is becoming very less. Is that clear?
Yes, ma'am.
Yeah. What would happen if it were a 2? Can lambda be 2?
Yes, ma'am. Lambda can take.
It can take any value, right?
Yes,
So
ma'am.
you can see the distribution changes according to lambda. This is the average, right?
Yes.
Yeah. Average number. So this is what a Poisson distribution does. And a Poisson distribution basically is my PDF visible?
Yes.
Yes, ma'am.
Yes, ma'am.
So when I want to know about a Poisson distribution, typically the problems will be, it will say that, okay, I have an average number of 2 accidents or 2 vehicles entering in a day. What is the probability that there are exactly 3 vehicles? Can I find that?
Yes, ma'am.
Yes,
Yes,
It would
ma'am.
be e
ma'am.
to the power of minus 3, 3 to the power of 3, or 3 to the power of 5 by 5 factorial. That is how I will find that. Is that clear?
Yes, ma'am.
Yes,
Yeah.
ma'am.
So that is what is about Poisson distribution. The expected value is lambda, the variance is also lambda. So the typical examples are number of vehicles, number of people withdrawing money. On an average, 3 people withdraw the money from a bank in a given day. So what is the probability that exactly 4 people withdraw this one? What is given to us? Lambda is given. What is lambda? On an average, 4 people withdraw.
4.
4.
It is 4. Okay, so that is how you can apply the Poisson distribution. Poisson distribution is counting the number of events occurring either in a fixed interval of time or in a fixed interval of space. So when it comes to discrete distribution, we started with the Bernoulli. We looked at the discrete uniform distribution. Then the binomial. Binomial is IID Bernoulli trials. Then we looked at hypergeometric. And then finally at the Poisson distribution. For each one of this distribution, you need to know what are the values this X will take. Here x takes only 2 values. Here it can take 1, 2 up to n. Here it takes 0, 1, 2 up to n. Here it takes, actually, it depends whether it takes 1 to n or whatever it is given. Here it takes 0, 1, 2 up to infinity. The probability mass functions of each of these, the cumulative distribution function, the expectation, and the variance. All this will help you to answer questions about the distributions. Any questions about discrete distributions?
I mean, Poisson distribution, if lambda going to be very small, then the probability is not going to the number 1, and the
No,
sum
no,
of
it is, see,
probabilities.
no, 1 second. Let me, is the Excel visible?
Yes, ma'am, yes.
Yeah. See, what I mean is, suppose this is very small. Okay.
Yes,
It
ma'am.
will add up to 1. But what I want, suppose it was 0.9. Let's look at 0.9. Okay.
Yes, ma'am.
The
Yes.
reason it is not adding to 1 is I'm not added 7 and all of that. It takes a value 7, but the probability would be very, very small.
Okay, okay.
Right?
Yes,
I'm
ma'am.
not added, it takes a value 7. On the other hand, if you look at it, say 0.2, you can see that right from 4 itself, it is taking a very, very small value.
Yes, ma'am, yes.
It is
Yes,
taking
ma'am.
a value, but the probability is very, very small, almost 0. That's what I want you to understand.
Yes, ma'am, understood.
Is that clear?
Yes, ma'am, yes.
Yeah. Okay. So that is about a Poisson distribution. Now we move on to a continuous distribution. So again, the three distributions we are going to discuss are continuous uniform distribution, a triangular distribution, and an exponential distribution. I think you do not have normal in your syllabus. That's what I have been informed. Now, just as we looked at a discrete uniform, I had probability x equal to x. I had it taking the value 1, 2, 3 up to n. Here in a continuous distribution, I don't have it taking discrete values. Rather, I'm telling it will be in this interval a to b. And the chance of finding this random variable in this interval is going to be the same. In other words, this is going to be the same. The chance of it finding x in this interval is the same. So it is uniform. Is that clear? So I
Yes,
need
ma'am.
to know what is this chance. Suppose this is a k, okay, and this is a probability density function. This is the, what is will be the area under this curve?
Integral.
If this value is k, if the
1
probability
by
density
a
function, what would be the area under this curve?
integral a to b.
1, ma'am.
Integral a to b of what?
Of
Integral a to b of k into dx, right? Okay. But what is the area under this curve?
K into B minus A.
Ma'am, it
1.
will be addition of yeah.
K into b minus a, that is the area of a rectangle.
Yes.
Right. And what should this k into b minus a be equal to?
1.
It will be 1. Why is it equal to 1? Because it's a probability density function. Agreed?
Yes, ma'am.
Yes, ma'am.
Yes.
So what is the value of this k?
1 by B
1
minus.
by b minus a.
1 by b minus
B
a.
minus.
So if I have a uniform distribution between a and b, what is the density of the distribution? It will take value 1 by b minus a if x lies between a and b, 0 otherwise. Is that right?
Yes,
It is 0 everywhere else, right? This function is taking the value 0 everywhere else. Till here, is it clear?
Yes.
Yeah. It is taking the value 1 by b minus a for all the x between. What would be the probability x is equal to a? Can I define a probability x is
No.
equal to a?
0.
It is 0, right? Because it's a continuous random variable. I can only talk about, can I ask about what is x belonging to CD?
Yes.
Where C is greater than A is less than C is less than B?
Yes.
That would
Yes.
be this area, right? If CD, that would be this area. Agreed?
But
Yes,
why
ma'am.
is it 0, ma'am?
See, because it's a continuous random variable, I do not talk about x taking a particular value. I always say x belongs to an interval, infinitesimally small interval. I don't define x takes a particular value. Is that clear?
Okay.
Yeah.
Yes, ma'am.
Okay. That is the biggest difference between a continuous random variable. So that density, so this does not matter whether it's a is less than or equal to x is less than or equal to b, because x taking a value a is 0. So these two are the same. Okay. Now,
Ma'am,
yeah.
Ma'am, does that mean, suppose the interval is 2 to 3, so does that
Yeah.
mean that 2.1, 2.2, 2.3 up till 3 will have the value 1 by a minus b?
See, I do not define a probability x equal to 2.1. Suppose a is 2 and 3. I can ask what is the probability x is less than or equal to, I can ask this, 2 is less than or equal to x is less than or equal to 2.5. What would this be? It would be 2 to 2.5. What is my b minus a? It is 1 into dx, which is, so I can, this would be the area, right? It would be just 0.5. Is that right?
Yes, ma'am.
See, I have 2 to 3. And I know that this is the, so let's look at it. You answer the question. Here it is my x. This is my f of x, right? I have x taking a, this is the value. It is a continuous value. You're saying, can I define what x equal to 2.1? I cannot define because x is taking value in this interval completely. What is the probability? X belongs to this interval with the same probability. Is that clear?
Yes, ma'am.
I'm not defining that it is, in the earlier case, I knew that x took the value 2. I could say 2.1, 2.2, 2.3, but it would also can take 2.11. It can take 2.12.
Means it can take any value.
Any value in that interval. That's what we mean. Is
and
that
we
clear?
don't know what it would be.
Could be multiple values, right? That's why I'm saying it could be very, very small, all these values. So I am replacing this with the area under the curve rather than discrete values.
So, ma'am, it would not be exact. It will be approximate value, the answer.
Which one? So I cannot define what is the exact value. Rather, if I want to know, I can ask what is the probability x is between 2 and 2.5. This would make sense for me.
Yes, ma'am, understood.
Right? And what would that be? It would be this area between 2 and 2.5. That would be the area. That's it. Is that clear?
Yes.
Yeah.
And can you give us an example
of what?
Of this
Yeah.
x.
Yeah, see, for example, I am telling you the time you take to, okay, the time you take to study is anything defined, or the time you take to reach from your office to home or home to college, whatever it is a uniform random variable which is between 0 and 30 minutes. Okay. So what is your A here and what is your B here?
0 and 30.
0 and 30.
0 and 30 minutes, right? I'm asking what is the chance that, so x is a random variable, and what is this x? X is the time you take to reach. Agreed?
Yes, ma'am.
Okay, right. I'm asking what is the chance that you will reach within 15 minutes. So what am I asking? Probability x is less than or equal to 15?
Yeah.
Is that right?
Yes,
ma'am.
Okay. So what is that I have between A is 0, B is 30. So what is my f of x? My f of x is going to be 1 by 30.
Yes.
So probability x is less than or equal to 15 would be 15 minus 0 into 1 by 30.
Yes.
Which is going to be 1 by 2 or 0.5 chance.
Yes, ma'am.
Right? What is that? Is that clear?
Yes, ma'am.
What is the chance that you'll reach within 30 minutes?
X is less than 30.
What would that be?
1.
1.
1, ma'am.
Because I know that you'll come within 30 minutes, right? What is it?
Yes.
Is that clear?
Yeah.
You
Yeah,
get
thank
it?
you.
If
Yes, ma'am.
someone is asking like time to reach at on 15 minutes, exact 15. It is not defined here, no?
So that if it is said, see, I'm not saying exactly 15 is not defined because that is not the question. It's a continuous random variable. I cannot talk about it taking exactly 15 minutes. Is that clear?
Yes, ma'am.
Yeah. Is that clear, please?
Yes, ma'am. Makes sense.
Yes, ma'am.
Thanks.
Yes.
Okay. So now one of the things is if my A is 0 and B is 1, okay, that is called a standard uniform distribution. Okay. And this is very, very useful, especially if you are going to go into your advanced courses. You will be talking about something called generating random numbers and everything. So when I, for example, let me go back to my Excel. Is my Excel visible? Yeah.
Yes.
So if I just type rand, I get a random number which is uniformly distributed between 0 and 1. Okay, so I'll just keep typing this. So I'm getting a, so you can see that this rand function will always return a uniform random number between 0 and 1. Okay, so the chance of it, so I'll get a complete set of random numbers which will lie between 0 and 1. This is called a standard uniform random variable. So what is my density here? It is just 1 by b minus a. B is 1 and a is 0. It is just going to be 1. Okay, 0 is less than x is less than or equal to 1. And this is 0. Otherwise, this is my density function. So the standard uniform random variable is something which is very, very important role. Especially this plays a very, very important role in simulation, namely in random variate generations. The next important thing which we are going to see is what is the cumulative distribution. Remember, when we looked at a cumulative distribution of a discrete random variable, I had nothing till it was 0. Then it was 1 by 2. At 1, there was a jump. There were discontinuities. So when I talk about a discrete distribution, my distribution, the cumulative distribution function is not a continuous function. It has jumps, it has discontinuities. It is what I call a step function. Is that clear? Yeah? Yes? Hello?
Yes, ma'am.
Yeah.
Yes, ma'am.
Whereas now for a cumulative distribution of a uniform distribution, I know what is my f of x. My f of x is 1 by b minus a if x is uniform a to b. Agreed?
Yes, ma'am.
Okay, so suppose this is my a and this is my b. I know that this is my density function is 1 by b minus a, my f of x. Now suppose c is here less than a. What is f of x? F of x is probability x is less than or equal to x. For all the values, so this is going to be minus infinity to x, f of x dx for a continuous distribution. Agreed?
Yes, ma'am.
Yes,
So
ma'am.
cumulative distribution function is the area between minus infinity to this x, f of x dx. What is my f of x? For x is less than or equal to a, what would be my f of x?
0.
Density. It is 0. So for any x that is less than or equal to a, what would be my cumulative distribution function?
0.
It would be 0. Would you all agree?
Yes.
Yes?
Yes, ma'am.
Yes, ma'am.
Right. So for x is less than a, f of x would be 0. So it is going to remain 0 at x equal to, so now at x equal to a, what is my f of x? I know that it is x minus, it would be so. When I have, so I have, suppose I'm looking at uniform 2 to 4. For x is less than 2, what was my f of x? It is 0. Till here, are we clear?
Yes, ma'am.
Right. Now let my x or let my x be between 2 and 4. Okay. So my f of x is going to be 2 to, it is defined minus infinity to this x f of x dx. Agreed?
Yes, ma'am.
This is minus infinity to this x. This is 1 by b, 4 b minus a dx. If it is a to b, this will be 1 by b minus a.
Yes.
Agreed? F of x is minus infinity to x, f of x dx. Or let me put it f of y. Okay, too many x's we don't want. Till here, is it clear?
Yes, ma'am.
Yes, ma'am.
Right? Now, if I have a x which is uniform between a and b, for anything less than a, it is going to be b. So I can write f of y to be a to y f of x dx. Would you all agree?
Yes,
Because
ma'am.
everything less than that will be 0. Till here, is that clear?
Yes, ma'am.
Yes.
But what is f of x? It is 1 by b minus a.
Yes, ma'am.
What is integral 1 by b minus a? So
It is
that
a
would be, what would this integral be?
ma'am, constant will come out.
Constant. So it would be just y b minus a by b minus a. Is that right?
Yes, ma'am.
Agreed?
Yes,
Yeah.
ma'am.
So I have f of y is 1 by b minus a y minus a by b minus a. This is equivalent to your equation, which is my plus c. Agreed?
Yes, ma'am.
What is this m? That's the slope of the line. So for any y which is between 2 to 4, I'll get an equation which is m 1 by b minus a. So you can look at this. What is b minus a in this case? What was my a in this case? It was 2. B was 4. 1 by b minus a is half. So you can see that this is the slope of that line. So it is continuous. For x is less than 2, it is 0. Then I'll have a line till it is 4. Then it will be 1 beyond 4 because it is, what would it be? It would be a to 5. A to 5 would be 1, right? What is integral 2 to 4 1 by 2 dx?
It's 1.
It is 1. So what will 2 to 5 1 by 2 dx be? That will
It's
also
also
be 1.
1. Yes, ma'am.
2 to 6 will be 1. So after for 4, it is going to remain 1. So this is what for any cumulative distribution function, and this can be for any b and a. I'll have till it is a, it would be 0. Between a and b, it would be a continuous straight line with slope 1 by b minus a, and beyond b, it will take the value 1. This is the cumulative distribution function for a uniform distribution. Is this clear?
Yes, ma'am.
Yes, ma'am.
A second. Okay, so that is about the uniform distribution. The expectation of a uniform distribution is a plus b by 2. Okay, this can be easily verified. And the variance is b minus a. So the variance is b minus a whole square. It's not b minus a square. It is b minus a whole square by 12. That is the variance of a uniform distribution. So the type of problems you would have done is, suppose x is a uniform distribution over 0 and 1. What would be probability x is greater than 1 by 3?
1 minus
X is
2
less than 1 by 3.
1 minus 1 by 3.
So I know that this is either 1 by 3 to 1 dx, okay, which is 1 minus 1 by 3, okay, or it is 1 minus 1 by 3 to 1. Again, that would be also 1 minus 2 by 3. You're going to get the same value. Is that clear?
Yes, ma'am.
Yeah.
Yes, ma'am.
X is less than or equal to 0.7. It's the same thing. 0.7. 0.3 is less than x is less than or equal to 0.9.
0.9 minus 0.3.
Which is 0.9. What would this be? Would it differ?
No.
No, ma'am.
It would be the same, right? Okay.
Yes, ma'am.
Okay. So where do you apply the question? And this is an application which we did even in the notes. So you have to meet a friend at 2 p.m. While you are exactly on time, your friend is always late and will arrive at the meeting place at a time uniformly distributed between 2 and 3 p.m. So if X is the amount of time you wait, what is the distribution? How much time would you wait? If I'm looking at X is the amount of time you're going to wait in minutes.
0
Okay,
to
what
60.
is the distribution?
Maximum 60
If your
minutes.
friend arrives at 2 p.m., how much time are you waiting?
0.
0.
0 minutes. If your friend arrives at 3 p.m.,
60 minutes.
60.
so would you accept that this X is uniformly distributed between 0 minutes and 60 minutes?
Yes.
Yeah. So what is the probability that you'll wait for at least for 30 minutes?
1 by 2.
1 by 2, because this is 0 to 60. Okay. And what is going to be your PDF? It will be 1 by 60. At least 30 is this area. Agreed?
Yes,
Right?
ma'am.
Less than 15
Yes, ma'am.
is going to be this area. Between 10 and 15, you can find out, right? This would be 10 and 35 would be this area. Not that area, but this area. Okay. So between 10 and 35 would be, this is my 0, this is my 60, this is my 10, this is my 35. This would be the area. And less than 45, you can easily find out the solution that greater than 30 is 1 by 2, less than 15. Between 10 and 35 is 5 by 12, less than 45 is 3 by 4. Okay. Is the uniform distribution clear?
Yes,
Yes.
ma'am.
Yes, ma'am.
So the next thing is, now if you look at it, now we are looking at what is called a triangular distribution. Now, when we look at a triangular distribution, the example is, now it is 2 p.m. and Joanne is planning to study till 6 p.m. But she knows that she will probably have interruptions and thinks that the amount of time she will actually spend is a random variable whose density curve is given as follows. So what does it mean? If she had that between 2 and 6, the time is uniformly distributed, the shape of this would have been, that is between 2 and 6, 0 to 4 hours, it would have been a uniform distribution. But she's not expecting it to be a uniform distribution. Is that clear? Okay. So what is the shape of the density here?
Triangle.
It is a triangular distribution. So what is the probability that X, so what is the probability that X is going to be less than or equal to 2 here? If I give you the shape, what is this height? What would be the area under this triangle?
Whole triangle.
What would be the area under this triangle?
1.
4
1.
units.
If the area under the triangle is 1, what would be the
Half.
height of the triangle?
Half.
1.5.
How?
Ma'am, we'll apply the formula half into base into height is equal to 1. Base is 4.
Okay. Half
and
into, what is your base?
4.
4 or
And height h is equal to
height
1.
is equal to 1. So what is your height?
1 by 2.
1 by 2?
Yes, ma'am.
Okay. So how would you find out what is the probability that she'll spend less than 2 hours?
Half.
What is the height?
Ma'am, height would be 2 and base is 1.
Height would be 2.
No, ma'am. Height would be 1.
Height
Height
is 1 by 2.
Height
What is the
1.5 and
area of
base
this
2.
triangle?
0.5.
1.
Half into, what is the area?
1.
1.
So what is your base?
4.
So what is your height?
1 by 2.
Half.
1 by 2.
Half unit, right?
Yes, ma'am.
Agreed. What is the probability that she'll study for more than 3 hours? That would be this area.
Yes, ma'am.
Yes.
That is going to be what?
1
1
by
into 0.25,
1 by
right?
2 into 1
Yes,
into
ma'am.
0.25. Yes, ma'am.
Right. So that would be
1 by
1 by 8. Probability that she'll study between 1 and 3 hours.
1 by 2.
1 by 4. We can minus
3 by 4.
3 by 4.
How would you do that?
Ma'am will minus the area of the
You know
rest
this probability and this
triangle
probability,
from
you
the
can
total.
just minus that
Yes,
and you
ma'am.
can do it. It is 3/4. Is it clear?
Yes, ma'am.
Yes, ma'am.
Yeah. So now this is a simple case. We did not go into the theory. This is what we call a symmetric triangular distribution because it is symmetric. Okay. But I could also have a distribution which is like this. These are not symmetric triangular distribution. Okay. So typically when I talk about a distribution, I need to know what is the slope of this and what is the slope of this. I have a triangular distribution wherein I can, just as I got the distribution here, f of x in terms of the parameter a and b, I can define a distribution, but I just am leaving that out of this particular syllabus. For a triangular distribution, you'll be just given problems of this kind where you can compute. The Prashant, they don't know about the triangular distribution with the parameters, right?
No, ma'am. We have discussed only basic thing. I mean,
Only this, right?
yeah, yes,
The base case, right?
yeah.
So this is about the triangular distribution. Given this, you can easily find out. You can see that I don't have a uniform distribution, but I could have something which looks like this, which is a triangular distribution. One of the most important distributions, again a continuous distribution, is what we refer to as an exponential distribution. Now see, whenever, especially when you are going to do a queuing theory part, okay, and you are looking at the distribution of what we say inter-arrival times. That is, when I have people entering a particular queue, the time between the arrival of the first person and the second person and the second person and the third person, that is what we call the inter-arrival time. And I also have a service time, that is the time taken to serve a particular person. That is what I call a service time. In many of the queuing systems, this inter-arrival time is it variable or will it always be fixed? What do you think it would be? The time of arrival between any two people in a queue.
Ma'am, it will be variable.
It would be variable. Similarly, the time taken to serve a person,
It's also
that's also variable. Is it deterministic or do you think there is some randomness?
Random.
Yes, ma'am.
So the time is a random variable. Would you all agree with me?
Yes, ma'am.
Yes.
And this random variable in many of the queuing applications is assumed to have a what we refer to as an exponential distribution. So a continuous random variable, the probability density function is given by lambda e to the power of minus lambda x is said to be an exponential random variable, or it's said to be exponentially distributed with parameter lambda. So you can see that the graph of this for various values of lambda, it is an exponential distribution. Okay. So you can see how the graph of this exponential distribution looks like. So what would be the CDF? I know that the exponential distribution, the PDF is lambda e to the power of minus lambda x. So for any x less than or equal to a, why have I taken it from 0? Because the range of this is only, what is the value of any x less than 0 in this case? It would be 0. The density would be 0. Agreed?
Yes, ma'am.
Yeah. So my f of x is 0 to a lambda e to the power of minus lambda x. Now what is your what would be the derivative of this? That would be minus e to the power of minus lambda x. Agreed? Divided by lambda, lambda and lambda would cancel out. 0 to a. So I get that is nothing but 1 minus e to the power of minus lambda a. Is this clear?
Yes, ma'am.
Yes, ma'am.
The CDF of an exponential distribution is 1 minus e to the power of minus lambda a. Okay, and this is how the graph. Again, the graph is for different values. You can see all of them cut off at 1. Beyond a particular point, it will. Can I have a CDF which is like this?
No.
Why not? Because always probability, because CDF is a probability. And what is the range of any probability? It is between 0 and 1. So you can see that any CDF should lie between 0 and 1. Is that clear?
Yes, ma'am.
Yeah. What would be the expectation? The expectation of a exponential distribution is 1 by lambda. Variance is 1 by lambda square, and this we can show through integration by parts. Okay, the mean and of the exponential is the reciprocal of the parameter, whereas the variance is the mean square. So let's look at an application. Suppose the length of a phone call in minutes is an exponential random variable with parameter 1 by lambda equal to 0.1. What does this mean? What is the average number? What is your mean average number of phone calls?
0.1.
Lambda is 0.1.
0.
What is the expected value?
1 by
0.1.
What is 1 by
No.
0.1?
10.
10 minutes.
10. Okay, that is how. So if I don't give you the parameter, but I give you on an average, there are 10 people arriving. Can you find out what is the parameter?
Yes, ma'am.
That would be 1 by 10. Is that clear?
Yes, ma'am.
Okay.
Yes.
Now, if someone arrives immediately ahead of you, what is the probability that you'll have to wait for more than 10 minutes? Probability X is greater than 10. What is your lambda? It is 0.1. Okay. What is probability X is greater than 10? It is 1 minus probability X is less than 10. Do I know what is probability X is less than or equal to 10? That is nothing but f of 10, which is 1 minus e to the power minus lambda a. Is that right?
Yes, ma'am.
So this would be 1 minus e to the power of minus lambda a. What is my a? It is my 10 lambda, which is just going to be e to the power of minus 10 lambda. My lambda is again 0.1. So it is going to be just minus e to the power of minus 1. Is that clear?
Yes, ma'am.
Yes, ma'am.
Now between 10 and 20 minutes. So I want X, probability of X is less than or equal to this one. What would this be? It would be f of 20 minus f of 10. Would you all agree?
Yes, ma'am.
Yes, ma'am.
F of 20 is 1 minus e to the power of minus 20 into 0.1, which is minus 2. Right?
Yes, ma'am.
F of 20 is 1 minus e to the power of minus 2 minus 1 minus e to the power of minus 1. So it is e to the power of minus 1. Right? Minus e to the power of minus 2, which is approximately 0.233 minutes. Is this clear? How you can apply the exponential distribution?
Yes, ma'am.
Yes,
So
ma'am.
remember one thing, the difference is here I'm looking at the distribution of the amount of time. In POSA, I was interested in knowing at the number of events in an interval of time. There is a difference in these two. Here I'm looking at the distribution of the time itself. In POSA, I was interested in knowing as the number of events in an interval of time. Is that clear?
Yes,
Yeah.
ma'am.
Yes, ma'am.
Yes, ma'am.
When I'm looking at the distribution of time, it would be an exponential. It is a continuous because I'm measuring the time. Whereas in POSA, I was looking at the number of events in an interval of time. I was counting the number of events in an interval of time. That would be a POSA or a discrete distribution. Is this clear?
Yes, ma'am.
Yes, ma'am.
Ma'am, in this
Yeah.
example, can we take one example like Poisson distribution? What will be
Here
the
you cannot
distribution?
take Poisson because what are you interested in? You're interested in knowing that you'll wait for more than 10 minutes, right?
Okay.
Agreed? So what
Yes,
is the variable of interest here?
time.
Time. And what is time? What kind of a variable is time?
Continuous random.
It is continuous, right? Okay.
Yes.
So if you're asking for the same thing, suppose I'm asking you that, okay, if I'm telling you the following, that I'm running a call center. Okay. I'm
Okay.
running a call center wherein people arrive at this call center with a particular that is, I have about 10 people arriving in a day for this telephone booth. Okay.
ma'am.
I want you to answer that what is the probability that exactly 3 people would come in a day to this telephone booth. So what is the distribution that you would have?
Poison.
Poisson.
It would be a Poisson because I'm asking you How many
Number
number
of
of people who arrive in a day? Whereas here I'm asking you, what is the distribution of the time that you have taken? Do you understand the difference between these two?
Yes, ma'am.
Okay. Right.
So whenever we are asking about time, it will be a continuous random variable.
Yes, measurement. So whenever you are measuring, time is something that you measure, right? You don't count the time. You measure, right?
Yes, ma'am.
Whereas whenever you are counting, it would be a discrete random variable. Is it clear?
Yes, ma'am.
Yes, ma'am. Got it.
Yeah. Okay.
Ma'am,
So
in both the variables, the lambda represents the average number of events happens in the time interval, no?
lambda in Poisson is an average. In exponential, it is 1 by lambda. Exponential average is 1 by lambda. Okay, so when you're looking at the average of an exponential distribution,
Yes,
the
ma'am.
parameter is lambda, but the average is 1 by lambda. The variance is 1 by lambda square. When you have a
Oh,
Poisson
okay.
with parameter lambda, the expectation is lambda and the variance is also lambda in a Poisson.
Okay, ma'am. Okay. Understood.
Okay.
Yes, ma'am.
Right. So what is it that you need to understand when you're looking at distributions? First of all, whenever I say X is a random variable, from the context, find out whether it is a discrete or a continuous random variable. How would you find it out? If I ask you for, if I'm typically asking you for the following. Okay, number of accidents, number of spelling mistake, number of people, number of times, then it would be discrete. Whereas if it is a measure, you would have a continuous random variable. Till here, is it clear? Yeah?
Yes.
Right. The next thing is,
Yes, ma'am.
once you identify that, within discrete, depending on what is this. So when would it be a binomial random variable? If I can identify, for example, I'm giving you, I'll tell you a situation. I'm having people, all of you buy in Amazon? Okay.
Yes,
Yes,
ma'am.
ma'am.
Right. The
yes, ma'am.
probability of, or imagine that 100 people are visiting a store. Okay. And the probability of making a purchase is 0.3. Okay. 100 people are visiting a store and probability of making a purchase is 0.3. What is the probability that exactly 45 people make a purchase? What is is it a binomial experiment?
Yes, ma'am.
Why?
Ma'am, because there are two outcomes, either they will purchase or not purchase, and every outcome is independent of each other.
Each other. Okay. What is your N here?
N is
45.
N is 45. I say 100 people visit the store. What is the chance that exactly 45 people make a purchase?
0.3.
It's 100.
N is 100. What is your P?
Yes.
45. 0.3.
Or
It was 0.3 and I'm asking probability X is equal to
45.
45, which is 100 choose 45. P to the 45. 1 minus P to N minus X. Is that clear?
Yes, ma'am.
Yes, ma'am.
So first you need to have a binomial experiment. First find out whether it's a binomial experiment. Okay. Again, I'm giving you the same thing. I'm telling you that I have a store. Okay. And on an average, 10 people make a purchase. Okay. What is the probability that exactly 15 people make a purchase on any given day? What is the distribution that you
Pause
use?
on.
Why?
Ma'am, because we have to find number of people in a particular amount of time.
Interval of time. So you
Interval,
can
yeah.
see that the context is the same. All of them are making purchases in a store.
Yes.
But in one you used a binomial and one you used a Poisson. Is that clear?
Yes, ma'am.
Okay. And then we looked at the hypergeometric also. In the hypergeometric, typically it is when I am able to divide my entire set into a good and bad, and I'm looking at a sample And I need to know that in that sample, how many good or bad are there. That is where I am talking about a hypergeometric distribution. So you can see that I lose the IID when I have a hypergeometric. This is the whole idea of the hypergeometric distribution. Is that clear?
Yes,
And
ma'am.
you can see that the hypergeometric is can be viewed as a binomial depending on what is your M and N. At some point, it would converge, but it loses this IID distribution thing. Next, we went on to the continuous. We looked at a uniform distribution. We looked at the PDF and the CDF of a uniform distribution, which is just a line. What is the mean? The mean would be a plus b by 2 and the variance is b minus a whole square by 2. Then we looked at triangular distribution. A triangular distribution, we did not generalize it, but we saw how you can apply the triangular distribution. And finally, we looked at the exponential distribution. We obtained the PDF. The PDF is nothing but 1 by 1 minus e to the power minus lambda a. And the expectation is 1 by lambda. The variance is 1 by lambda square. So wherever this is given, you can compute the distribution. Okay. So I hope you all found this session useful. If there are any questions, I'd be happy to answer that.
Ma'am, regarding this expectation earlier in the discrete thing, you were saying it's the long run average. So for continuous, what will be the concept?
It would be the same idea. It is not only, it's a long run average. Be it
As in because n is not there no, in continuous. So I was a little confused about
what. N? No. What is an expectation? An expectation is nothing but, see, finally, whether it is a continuous random variable or a discrete random variable, you are mapping the outcomes of a random experiment to a real number. Is that clear? Either you're mapping it to a real number or you're mapping it to an interval.
Okay.
Let me describe two experiments. One is tossing a coin twice. What is your sample space? HH, HT, TH, and TT, right? The other experiment is the time taken for you to reach your office from home. What are the outcomes of this experiment? First of all, is it a random experiment?
Yes.
The time taken for you to reach office from home, or the time taken for a bulb to fuse, a good bulb. What are the outcomes of that? First of all, is it a random experiment?
Yes.
Yes, ma'am.
What are the possible outcomes?
1, 2, 3, 2.
0 to
Would it be
something.
1, 2, 3, or it would be an interval 0 to infinity?
0
Yes,
to
ma'am. It
infinity.
is an interval.
Any x such that x is between 0 and infinity?
Yes.
Right. So both of them are random experiments.
Yeah.
Here I am giving 2, 1. These are the values. These are discrete values this random variable is taking. Here I can tell about the discrete values a random variable will take is in the interval 0 to infinity.
Right.
The variable is counting the number of heads here. Here it is measuring the amount of time.
Correct.
Agreed. Now both of them are random experiments. So here, and I'm asking what is the expected value this x is taking? It is telling if it takes these values, what is the long run average? Right? Here it is a measurement of the time. So if I continue to this one, on an average, what would be the value this x is taking? Why wouldn't it be a long run average in that case also? See, here x for this experiment is taking 2110, right?
Right.
Yes.
How did I compute that? See, if you go back to an expectation of a random variable, okay. So what I had is this. So what is an expectation?
Long run average.
It is, for example, I think I don't have that slide here. It tells you what is a long run average, okay? And it's not only for, I have expectation defined for both continuous and discrete random variables, okay? Is it clear?
Yes.
Yes, ma'am.
Because I'm observing the same experiment. See, today you're coming at some point of time. Tomorrow you'll have the same experiment. So if I am continuing the same experiment, then what would be the expectation? That's what we are trying to see. Is that clear?
Okay. So it's about number of tries.
Yeah. No. It is not it is, yeah, but it is in some sense it's a long run average. That's why we say it's a mean and variance. We are equating it to the mean and variance as a parameter.
Got it.
Basically, it is telling you on what would be the long run. If I am continuing repeating this experiment, then what can I expect the average of that measure to be? Okay.
Right. Thank you.
Yeah.
Ma'am,
Ma'am.
if you find X as a number of hours, like it can be only counted in hours, then it will be discrete, right? For the bulk.
So give me an example. Yes. See, suppose I'm looking at the number, instead of looking at the number of minutes, I am calculating the number of amount of time I spend as a discrete. So it depends on how you're posing the question. I'm saying either I can study for 1 hour or 2 hours, but typically you don't measure time as discrete values, right? You don't count the number of hours that way. If you're counting it as number of hours as 1 hour, 2 hours, rounded off to the nearest random integer, then it would be discrete.
Okay, ma'am.
If you're not measuring it time as continuous, but you are rounding it off to the nearest integer, it would be discrete. Okay.
Yes, ma'am.
Is it clear?
Yes, ma'am.
But in that case, I need to specify that you're spending 1 hour and 2 hours or 3 hours and 4 hours is the same. So I can take either 1 hour, 2 hour, 3 hours or 4 hours, each with probability 1/4, 1/4, 1/4, 1/4. That is different from telling that I could take anything between 0 to, so this is 1 hour, so 0 hours to this particular time, 4 hours, it could take any time, that will be a continuous variable. Is that clear?
Yes, ma'am.
Okay.
Ma'am,
So
one more
it all depends on the context of the problem. How would you choose the distribution?
Ma'am, one more question. For hypergeometric distribution, if the number of trials is not big enough, like as compared to binomial,
okay,
why is the variance more for hypergeometric? Like I'm asking conceptually, like why
see,
is the
conceptually, that's what I'll say. See, the variance of a hypergeometric is this way.
Yes, ma'am. Like I get it by formula, but like just asking, why does it like act this way?
I'm not sure, because there's a finite correction that you're doing, right? That's the reason. Okay. There is this one, but I think I need more time to explain that. I'll try and see whether I can do it as an addendum thing. Okay, good question, but from the formula, it's very clear, right?
That makes sense, but
yeah. So I'll put from a conceptual level. I'll try and explain that. It will take more time. I think we are running out of time. I'm sorry, I cannot address that. Okay. Yeah. Any more questions for the exam part? Okay. If there are no more questions, I think thank you all.
Ma'am,
yeah,
just one more thing.
Yeah.
Ma'am, in continuous uniform distribution, we say f of x is the probability, right? F of
yeah,
x.
it is the probability. F of x, see, in any continuous distribution, your f of x is what we call the density function.
Yeah.
That same, see, again, the reason why we are differentiating it is referred to as probability distribution function. And what is distribution? How is my random variable distributed? If my random variable takes discrete values, it is what is the chance of that random variable taking a discrete value, probability x equal to x. If it's a continuous distribution, it is probability x belonging to a particular interval. That is what I call that is where I have, instead of x equal to x, I'm saying that it is an area, right? It is defined by a density function. Is that clear?
Yes, ma'am.
Ma'am, in Poisson distribution, expectation and variance are same.
Yes.
So what is the practical significance of these things? Like,
what do you mean by practical significance?
Like expectation is longer than average. So what Means variance we are seeing.
Variance is, see, basically what is the variability? See, expectation in some sense will capture where is your central tendency. Expectation is a measure of central tendency, right? And variance is a measure of your, basically it is the spread. Is that clear? Yeah.
Okay.
So that's, it so happens in the Poisson distribution, your expectation and variance are the same. That's what it is.
Okay. Thank
Okay.
you.
Yeah.
Thank you, ma'am.
Yeah. So
Thank
thank
you,
you all.
ma'am.
I'll share the slides with Prashant, but most of these slides are already available to you. It's just a revision. He will upload it in your, so Prashant, you can upload it in the dashboard. Okay.
Yeah, sure,
Thank
ma'am.
you all.
Sure.
Thank you, ma'am.
Thank you,
Thank
ma'am.
you all. Wish you all
Thank
the
you, ma'am.
best.
Good night.
Yeah.
Thank you,
Thank you
ma'am.
all. Wish you
Thank
all
you,
the
ma'am.
best. God bless. Yeah. Thank you.
Thank you, ma'am.
Thank you.
Thank you, ma'am.
Thank you all.
Thank you, ma'am.
Prashant sir,
Yes.
sir, can you please let us know, like, normal distribution is not coming in the
No, it's just in additional content. So I mean, it's not in the syllabus for this.
like that was such a huge part of the whole thing studied
Yeah. So only till exponential distribution will be coming in.
and no geometric as well, right?
No, not geometric also.
Okay, sir.
Yeah.
Thank you.